All right, welcome back, guys. In this video here will be the part 2 of 3.2 lesson measure of variation. In the previous lesson, we discussed how to compare two data set using the spread of the data values in each set. And we captured that concept using standard deviation. It is used to measure how much or how far data values deviate from the referencing point, which is the mean. The formula for that is this here. We can manually calculate it, but it's more tedious or complicated if the data set is large, meaning 100 values or 1,000 values. So it's more efficient if we use technology to compute the standard deviation. So now we're going to look at another use of measure variation. How do we use standard deviation to apply? Why is it important? So the next thing we have on the list would be it's called the range rule of thumb. This is what we use to identify data that are considered to be unusual or extremely large or small or outliers. So what it is it's the way we separate, or actually not separate, but kind of divide the data values in certain region. So let's say we have a quantitative data set and we can scale that on a number line, and we have, let's say the mean is in the middle. So let's say here's the mean, okay? And then we can find the standard deviations, right? So let's say we find the standard deviation. So we got mu and sigma, right? Then if we take the mean, we add it to 2 times the standard deviation. So 1 times, 2 times. So let's say this is sigma mu plus 2 times sigma. And then we can subtract 2 times standard deviation on the left hand side as well. So mu minus 2 times sigma. So now we have divided the data set in a way that any data values, any numbers that fall within the 2 standard deviation of the mean, we say that that's considered to be usual data values. Okay, or another word we can describe this is with not significant data value, not significant data values. So anything that within 2 standard deviation of the mean, they're just usual data values. Any data values that are extremely large or a little bit away from the mass majority of the data, meaning belong in the right or the left side here. If a data value that is on this side, we say that it is unusually high data value, or we can say that it is significantly high. Significantly high. And then over here is unusually low. Okay, or not significantly low. So one of those. Okay, so the range rule of thumb saying that anytime we have a data set, we can first find the mean and the standard deviation, and from there we can classify, we can identify. So range rule of thumb allow us to identifying okay, unusual data values. For example, if you walk down the street and you say, oh, this person is a bit tall. I mean, he is much taller than the average, and then we measure his height. So now he's 8 feet. One could say that, okay, this person is unusually high compared to the average height of a person, right? Something like that. So that's a little more subjective, but you can see that if we would have an actual data set, we can actually make it more objective, where we compute the mean and standard deviation and then classify any given data value. Is it belong to the 2 standard deviation from the mean, or is it exceed on the right and left side of the 2 standard deviation, the mean? So this allows us to identify any unusual data values. Okay, so that is the cutoff point right there. So this is called the range rule of thumb. Just a side note here, we can estimate the standard deviation using the range divided by 4, and the range is just max value minus min value, and then if we divide by 4, that gives us an estimate of the standard deviations. Okay, all right. So if we don't want to go through and do the calculation to find out the standard deviation of data set, if it's like a 2,000 data values, what we can do is we look at the lowest value and the highest value, subtract those two numbers, divide by how many there are. That gives us a good quick estimate of the standard deviation, and then from there we can discuss, how much the data value is spread. Okay. Another let's say the next thing we have is called empirical rule. So this is just something that kind of relates to range rule of thumb, but a little more on the mainstream, has to do with distribution that is approximately bell-shaped or normal. So this is only applied to bell-shaped distribution, okay? Whereas the range rule of thumb apply for any distribution. Okay, so the empirical rules say that given a distribution that is approximately bell-shaped, we can estimate the percentage of data values fall within certain number of standard deviation of the mean. So they say that all the values fall within one standard deviation of the mean is about 68%. And if it's two standard deviation of the mean is 95%. And then 99.7% if it's three standard deviation of the mean. This means, in terms of picture, let's say we have a data set, okay, and that data set is approximately bell-shaped, so maybe it looks like this here, right? So approximately bell-shaped. We're saying that data set will contain 68% of data values within the one standard deviation of the mean. So let's say here's the mean. The mean is the measure of center, so right in the middle of the data set. So this is the mean. Okay, so we're saying that let's just use X bar here because this is empirical rule. This is based on observations. X bar, which is the mean, right? So let's say here's the mean, and if we go one standard deviation to the right and to the left of the mean, okay, so let's say this is X bar plus one standard deviation, X bar minus one standard deviation, okay, then this area, or from left to right of one standard deviation of the mean, we're saying that the empirical rule is saying that about 68% of the data value, okay, about 68 of the values fall within the first standard deviation of the mean. Okay. So now if we go one more standard deviation to the right, red here. So let's say this is X bar plus 2 times standard deviation, X bar minus 2 times standard deviations. All right, so now this cover 95% of all data values. Okay, so if we extend the borderline to 2 standard deviations to the left and to the right of the data set, we can approximate that all 95% of data values fall within the 2 standard deviation. And if we go one more, X bar plus 3 times standard deviations, X bar minus 3 times standard deviation. Okay. Then from that to that there, about 99.7 data values fall within 3 standard deviation of the mean. Okay. So again, the empirical rule only apply to the distribution that roughly resemble a bell-shaped curve. This becomes very important when we look at probability and look at this percentage of people fall or satisfy a certain event or certain requirements. Right now it's kind of hard to see how has this become useful just yet. But here's some example that we can try here to kind of see how the empirical rule being applied here. So it says that a certain group of test subjects had pulse rates with a mean of 77.8 7 beats per minute and a standard deviation of 10.3 beats per minute, would it be unusual for one of the test subjects to have a pulse rate of 138.3 beats per minute? Okay, so we're not given whether the distribution of pulse rate is bell-shaped or not. All we're saying that there's a mean, there's a standard deviation, and then given a data value, is this data value or is this test subject pulse rate considered to be unusual or not? Okay, so we said we said data. So we said data. The data will be a certain group of test subjects. So we said data in this case will be pulse rates, and the pulse rate just come from a selected group of people. So it's not quite the population. So that's the data. Okay, we have X bar because it's sample, right? 77.7 BPM. Standard deviation will be S because it's sample. 10.3 BPM. Okay, so that's the data and the X bar and the S. So we're asking, is X or given test subject of 138.3 BPM unusual? Okay, that's what we're asking to do. Okay, well, we can use the range rule of thumb. We can't really use the empirical rule to identify this is unusual or not because we don't know the distribution of this pulse rate. Is it bell shape or not? We don't know, but we can apply the range rule of thumb because that is applying for all type distribution. Well, to do that, we need to know whether 138.3 is past the 2 standard deviations or not, or is it right in the middle? Okay, let's find out. So we're going to draw the range rule of thumb for this pulse rate distribution. Okay, so we say that here is the mean, X bar, which is, okay, 1, let's do, so X bar is 77.7, and then X bar plus 2, standard deviation will be 77.7 plus 2 times 10.3. Okay, what would that be? Let's do the calculation real quick. So 77.7 plus 10.3 times 2. So that is 98. 98.3 is the cutoff value for the 2 standard deviations. So the given pulse rate, so X equal to 138.3 is somewhere in this region here, past the 2 standard deviation. So we're gonna say is unusual high pulse rate because it is more than 2 standard deviation above the mean. Okay, so that's how we answer that question. All right, let's do one more. So now in exercise 2, we are working with bell-shaped distribution. That's what we're given right here. IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. What percentage of IQ score between 70 and 130? So this is saying that the data we are working with is IQ score. And it doesn't mention whether it is IQ score of a certain group or more than just a few individuals. This is IQs in general. So we can go ahead and assume that this here is a population. So we're going to say population data. So therefore a mean is denoted as mu. So the mean is 100. Standard deviation is not S, but is sigma because it's populations. 15. So that's the data. And we also given that it is bell shape. Roughly bell shape. So we're gonna draw a normal distribution and then label the 100 in here. So that's mu. Okay, and then we're gonna say, okay, what percentage of IQ scores between 70 and 130? So we can say, okay, 130 is 2 standard deviation above the mean. So that's 130. So 130 is right here. That's mu plus 2 times sigma. And then 70 is mu minus 2 sigma, right? Would you agree? So this area here, okay? So if you take 100 minus sigma is 15, so that's 2 times 15, that's 70, which is 2 standard deviation below. And then 100 plus 2 times 15, that's 130. So that's 2 standard deviation above the mean. So according to the empirical rule, if it's 2 standard deviation above or below the mean, that's 95%. So we say 95% is from there to there. So to answer this question, we said about 95% of IQ score IQ scores is between 70 and 130. Okay, so another way of looking at this is, we can say, oh, this person has an IQ score of 120. We can say that person belongs to 95% of the population's IQ score. Or if a person has an IQ score of, let's say, 145, so let's say if a person has an IQ score of 145, we can say that, okay, this person is smarter than 95% of the people, or is in the top in a certain percentile. And that's what the next lesson is, the measure of position, to figure out what position of this compares to the rest of data values. So that's kind of interesting. I'm gonna let you guys work on this example on your own here, okay? But I will give you the answer just in case you want to check the answer here. I don't know. I have the answer here. Actually, we can just do this on Zoom call here. I'm gonna end on this note.